to plot along this line. So we'll get how temperature varies along the thickness and with time, that's also included. So when we apply plot, so this is the temperature that we get. Hello and welcome back. In today's video, what we are going to do is we are going to move one step ahead. Till now, what we did was we solved problems that were assumed to be steady state. There was no problem was studied that involved time. So what we are going to do today is we are going to choose a simple one-dimensional problem, and we are going to study the change in temperature at a point with time. So in other words, we are going to choose a time dependent problem, transient problems. So our problem here is we have a plane wall with thickness 0.1 meter, which is initially at 300 Kelvin. So we have a simple wall here. The entire wall is initially at 300 Kelvin, and now this end is suddenly raised to 400 Kelvin temperature, and the other end as well as these two ends, to make sure the heat transfer is one dimensional, the other end is kept insulated. Now we are going to solve this kind of problem, and the material is aluminium. We are going to see how temperature varies from point to point along the thickness, as well as how temperature is going to vary at a particular point with the time, hence transient heat study. So we know, since it is one dimensional and transient, we can derive the governing equation, or we can write the governing equation. We know the general governing equation for heat transfer is rho Cp dou T divided by dou T is equal to divergence of K del T plus Q dot generation. Now we know, since problem is transient, so we have to keep this term. Now till now we were assigning 0 to this term because of the steady state condition. Now since it is one dimensional, so this one is going to reduce to dou by dou x. If we consider this x direction, dou by dou x of K dou T by dou x, and we are going to assume there is no heat generation for the simplicity of this problem. So what we are left with is this particular equation. So we are left with now also we'll consider, for simplicity, we'll consider the constant thermophysical properties. So K here is constant, so we are left with K dou 2T divided by dou x2 is equal to rho Cp dou T divided by dou T. This is the governing equation for this particular kind of problem here. Now we have this equation over here, governing equation, dou T divided by dou T is equal to or we had Cp rho Cp dou T by dou T is equal to K dou 2T divided by dou x2. Now if we find dou T by dou T, so we will divide the rho Cp dou 2T divided by dou x2. Now this term here is alpha, we call it diffusivity or thermal diffusivity. Dou T divided by dou T is equal to thermal diffusivity times dou 2T divided by dou x2. Now this thermal diffusivity basically means how heat spreads inside the material. What we have here is we have this equation and we have to solve this, and our material is aluminium, and these are the properties that we are going to take. Now thermal diffusivity is equal to, as we saw, K divided by rho Cp, and when we do K divided by rho Cp we get alpha value this. Now what are our boundary conditions here? We know one side is at 400 Kelvin. This is our boundary condition, and initial condition is entire wall is initially at 300 Kelvin. This is our initial condition, and other end is insulated. So we have our conditions here. initially whole domain is at 300 Kelvin, and left hand side is at 400 Kelvin, and right hand side is insulated, which means heat flux is zero, and which reduces to this thermal gradient at x is equal to L, because this is x is equal to 0, this is x is equal to L. So here no heat flux is there is no heat flux, so we get T dou T by dou x equals 0 at this location. Now when we apply this boundary condition, what we get is this particular equation. Now for a plane wall with one surface at constant temperature is the left side and other is insulated, so the solution, this above governing equation, when we solve it analytically, we get this solution, which is in the infinite series form again. Now here we can see there is a number, dimensionless number called Fourier number, and we know from the theory that if this Fourier number is greater than 0.1, we can use the first term approximation. This very first term where n is equal to 0, we can take only the first term, n is equal to 0 term, and with that term will contain all the accuracy that we need for practical purpose, provided Fourier number is greater than 0.1. So we need to find a Fourier number first. Now Fourier number by definition here is alpha t divided by L square. So we use alpha equal to that we calculated here is alpha is over 9.75 10 to the power minus 5, and then we have time. Let us say we want to find the temperature at the mid location. This is our wall where we suppose want to find the temperature at the mid location, which is entire length is 0.1 meter, so we need to find at 0.05 meter, and since a transient problem, so we need to find temperature at x is equal to this position and at time is equal to c 20 seconds. After 20 seconds we will find the temperature. Now till now what we were doing was what we used to do was we used to calculate temperature at a particular location. There was no involvement of time. Now temperature at a point is also changing with time, so temperature at this point and at this time. Now when we calculate FO, so alpha we have to multiply it with 20 divided by L. L is the entire thickness, which is 0.1 square. When we calculate Fourier number, it comes out to be 0.195, which is clearly greater than 0.1. So we can use first term approximation. That means we will use only the first term of this solution that will contain the our value up to higher accuracy. So when we put n is equal to 0, so this is 2 times 0 is 0, so we were left with 4 by pi. So we're left with here 4 divided by pi, then cos 0, cos of 1 by 2 pi x by L, cos pi by 2 and x divided by L, and then we have e to the power, this n is 0, 1 by 2 square pi square and f naught, so it is e to the power, n is obviously 0, so we have pi divided by 2 square, pi divided by 2 square is 4, and the Fourier number. So this is the first term approximation that we will have our solution within. So we have 4 by pi cos pi by 2, x is our location where we want to find this, that is 0.05, L is the thickness 0.1, then e to the power, this Fourier number is calculated as 0.195 calculated above. So this gives us dimensionless temperature as 0.56, and this dimensionless temperature is equal to our temperature that we are looking for minus the surface temperature, and which is 400, divided by initial temperature, which is 300, minus the surface temperature again, which is 400. So this entire value is equal to 0.56. So we know this is 300, this is 400, this is 400, this is 300 Kelvin, this is 0.56, so we can get the T of x comma t. So we find that T at the location 0.05 meter, and at time after 20 seconds comes out to be, when we solve this, it comes out to be 344 Kelvin, which is around 70 degrees Celsius. So this is we can see what this value is actually. So we have 344 minus 273, so this is 71, so this is 71 degrees Celsius. So we get analytical value of 71 degrees Celsius. Now we will go to COMSOL Multiphysics and solve the same problem using COMSOL and see what we get. Now we are inside the COMSOL Multiphysics. Now we'll open the COMSOL Multiphysics wizard. So we'll choose 2D here, but since we are going to insulate the other boundary, so it will become automatically become one dimensional. Otherwise we could choose a line, one dimensional geometry as well. We'll get the same thing. So this time, now till now what we would use to do, what we used to do were we was choosing stationary because there was no involvement of time. Now we have time, so time dependent. Now this is the COMSOL opening. So we'll go to geometry, we'll create our geometry, which is rectangle. We'll keep the width, which is our thickness, 0.1 meter is our thickness, and this is what we require for the problem. And height, let's keep it anything, we are not bothered about this. Let's keep it 0.8 meter. We'll build our geometry. Now this is our wall. Now what we also need to do is we will have to create a point where we want to find the temperature. So we want this point exactly at the center. So specify the coordinates. 0.1 divided by 2 is 0.05, and height is 0.8, so mid will be 0.4. Now this is our point. Now also what we want to do is we are going to create a line here, line segment, that we need for the purpose of plotting a graph. So we'll go to more primitives, then find line segment, then we'll choose the coordinates. So first coordinate will be at the left side, and second will be on the right side. So first coordinate will be at x is equal to 0 and y at 0.4, and second coordinate will be at x is equal to 0.1 at the other end and 0.4 again at the same height. So this is our line. Now this is the geometry that we need. Now material, we are not going to choose the material here. Uh, uh, we are going to choose the material from the solid. So what we are going to do is here. So here we have another option for choosing properties. For K, the thermal conductivity according to the problem is so thermal conductivity according to the problem here we have is 237 27009. So we have 237 thermal conductivity, 237 is thermal conductivity. This is 2700, 2700, and CP is 900. So this is the this is the material assigned. Now initially the entire system is at 300 Kelvin, so initial condition, initial temperature 300. Now the left hand side has to be applied with temperature boundary condition. So this is, and this, they are at 400 Kelvin, so 400 Kelvin, and rest are applied with this thermal insulation, which means this and this end. So moving forward, we'll mesh it, and we're going to choose finer mesh. Finer the mesh, more accurate the results are. This is the general rule, but we cannot go on making it extremely fine, because that will take a lot of time for the simulation to run, and which means more time means more money. So we have to find the optimum solution, which leads to the concept of something called grid independence test, or choosing the cell size, which is a different concept. We'll get there in later videos. So we'll go to time dependent. Now this is new, time dependent. Here we have to choose option. We'll start with x is equal to 0, t is equal to 0 time. We'll keep time step, say 1 second, and we will tell it to calculate for up to 50 seconds. So it will calculate, it will start at 0, then calculate next value after 1 second, then next value after 2 second, then next value after 3 seconds. So time step we are keeping 1 second. So when we compute this, when we solve this equation that we solved analytically using COMSOL, so it's solving for us. So what we have here is we get this solution over here, and what we want to find is we will go to derived values, point evaluation, we will choose our point, and we will convert the temperature into, say, degrees Celsius, and we'll evaluate. Now till now what we used to get was one value, because that was the temperature at this particular point. Now temperature at this point is changing with the time, so we have chosen up to 50 seconds within interval of 1, so there will be 50 values. If we see, so we have these 50 values. This is the temperature, these are the temperatures at this midpoint at initial time, then after 1 second, 2 second, 3 second, 4 seconds. Our time is 20 seconds, so we'll go to 20 second. We can see that at 20, after 20 seconds the temperature is around 69 point something, which is approximately, we can write it as 70 degrees Celsius. So using COMSOL we get temperature of around at 20, we get at 20 after 20 seconds we get 610, which is also around 70 degrees Celsius temperature. So after 20 degrees Celsius temperature, sorry, after 20 seconds the temperature at this midpoint will be around 70 degree Celsius, which we got from the analytical solution as well. So we can also plot how temperature varies using this line. So we can plot the temperature, how temperature varies along the thickness, as well as how it varies with time. So for that we'll go to results, we'll choose one dimensional plot set, we go to one dimensional plot set again and choose line graph, and we will choose units as degrees Celsius, and we will choose this line and tell the COMSOL to plot along this line. So we'll get how temperature varies along the thickness and with time, that's also included. So when we apply plot, so this is the temperature that we get. Now here we have to ignore the t is equal to 0 time, because this is something that we have also have to cover in a separate video, why there is this initial fluctuation. So this we can understand, if we want to understand in briefly, is that the entire domain was initially at 300 Kelvin and the left edge suddenly was applied with 400 Kelvin. So there was this temperature jump initially, which was not, the COMSOL equation, basic equation was not able to, you know, tackle that problem, and this initial mess was seen here, so which is obviously not a realistic case here. So we are going to ignore this t is equal to 0 second initial trend. The rest trends are same. This is after 1 second, this is after 2 seconds, 3 seconds, and up to t is equal to 50 seconds. So initially the entire domain is at, left side is at 400 Kelvin, which is around 127 degrees Celsius. Then the temperature decreases along the thickness in this manner. So this is the temperature, how temperature varies. If we take this one curve, this is the temperature, this is the variation of the temperature from left end to the right end. It decreases from 127 degrees Celsius to around 27 degrees Celsius, which is the initial value, and the trend is this. And these trends are for separate time. This is after 2 seconds, after 3 seconds, after 4 seconds, how temperature is going to vary along the thickness and all. That is all for today's video. Thank you.